Today we're going to be talking about gravitation. And now we've talked about gravity before, and we know that gravity is always downward and at the value of negative 9.8 meters per second squared. Now we're going to be taking it to larger scales. Okay, so instead of talking about gravity that is on the earth, like a ball being thrown up, which is a small ball as compared to the large size earth, we're going to be talking now about objects that are very large and proportional and very far apart. And so this is going to be Newton's universal laws of gravitation. Okay, so we're now going to be taking gravity as we know it, and we're going to be talking about big, huge planets and the sun and stars and satellites and everything else that's going to be in space. So we're going to be learning about planets and motion of the planets. Okay, so let's just first start with a little bit of a history lesson. There's three guys that we're going to be talking about: Nicholas Copernicus, Tycho Brahe, and Johannes Kepler. And these three have a really kind of an interesting background. So there's a little bit of a history lesson here. So a long, long time ago, before modern day, people believed that the earth was the center of our universe. And that came a lot from biblical reasonings and religion, because they wanted earth to be our center and not something else, that God made the earth the center of the human existence. And so everybody believed that all the planets, and all the stars, including the sun, all rotated around the earth. Well, there was a guy, Nicholas Copernicus, and he believed that the universe and its planets, everything rotated around the sun. But he wasn't able to prove it. He would study the stars. There was nothing else to do at night, no Facebook, no cable TV, and so he went out and he started looking at the planets and looking at the stars, and were able to track their motion and their movement. So in 1543, Nicholas Copernicus, and he's from Poland, he published a book that showed that the true motion of the planets and the motion of all the stars and everything in the atmosphere, including the earth, rotated about the sun. Now, for him, this was just a theory. He wasn't able to exactly prove it, but it made more sense mathematically. Before, he couldn't get the numbers to work out. If everything was rotating around the earth, how certain things fell into place at certain times of the year. And so he was able to do that. He was really reluctant to publish it because he was also, he worked for the church. And so there was a little bit of a confusion there, and he wanted to make sure that everything was okay. A lot of problems which contradicted what the church was teaching was what he was writing. So right before his death, he published this book. After his death, there was a Danish astronomer, Tycho Brahe, and he also used years and years of recording. He took Copernicus's original idea, and Tycho Brahe was able to put math behind it. And he took 20 years of recording the motion of planets and motion of stars, and he was able to come up with more mathematical background to prove what Copernicus was able to hypothesize. And so Tycho Brahe spent his whole life doing that research. But he still had a problem because he had everything was rotating except for the sun did not rotate around the earth. The earth did not rotate around the sun, but everything else rotated around the sun. He was still reluctant to push it that next step. And so close after 20 years of his research, he took on an assistant, and the assistant was Johannes Kepler. Now, Kepler was a German astronomer, so he moved up to the Danish territories, and he started working with Tycho Brahe. And Tycho, right after his death, Johannes Kepler was able to prove without a doubt what we believe today, that the sun is the center of our universe, and all the planets and all the stars and everything and comets, everything rotates around the sun. And he was able to do this. Now, there's been a little bit of speculation in history that Johannes Kepler actually killed Tycho Brahe, poisoned him, and there's been some controversy probably within the last 50 or 100 years of whether Johannes Kepler actually did kill Tycho Brahe and took all his work and made it his own. And it's kind of interesting because everything that we're going to be studying today is based on Kepler's laws. It's not Tycho Brahe's laws, but Kepler's laws, and so that's where the controversy comes about. So we're going to be really getting into Johannes Kepler's work and talk about that now. So Johannes Kepler came up with these 3 laws. They're called Kepler's law. The first law states that everything in the solar system orbits in elliptical orbits. So we're not orbiting in a circular orbit. These are elliptical orbits. And tomorrow in class, we're going to do a little bit of a lab on some of the definitions of an ellipse. An ellipse is kind of your oval, and it has 2 foci, which are going to be kind of like the 2 centers of a circle. But in this case, we have one over here and one over here. The elliptical orbits, the sun is one of the foci, and this is your planet that rotates around the sun in an elliptical orbit. So that's what his first, Kepler's first law states. Now, it doesn't have to be a planet. It can be the star, and it can be comets, or it could be a planet. So anything that's going to be rotating around the sun is an elliptical orbit. Okay, so that's Kepler's first law. Now, Kepler's second law is a little bit more confusing to understand. Kepler's third law says that equal area is an equal time. So if you have a planet, and each of these black dots is going to be the planet, and its rotation around the sun, and these are going to be equal time. So say, 1 month, 2 months, 3 months, each one of these times is equal. So the time that it takes for this planet to go from here to here is the same time from here to here. So if we were to actually do some geometry, the area covered in this time frame is going to equal to the area covered in this time frame. So T1 equals T2. The time it takes to get from here to here equals the same time from here to here, even though you can see this is a longer distance. So what's that going to tell you about the velocity from here to here? So think about that versus the velocity of here to here. Okay, if the time is the same, for this to cover more distance, it's going to have to go much faster than it would be over here. And the area, this whole area in here, is equal to this area here. So that's what Kepler's second law says, that a planet or a comet will cover equal areas in equal time. Okay, and then we have Kepler's third law. Okay, so Kepler's third law is actually an equation. Kepler's third law says that now T is going to represent the time, or what we call in physics the period, the time of one full rotation. So the time of one full rotation of the Earth around the sun is 1 year. Each planet has a different amount of the time it takes for them to go one full rotation around the sun. So this would be the time period, and D is going to represent the distance from the center of one planet to the center of the sun. Now, you can see back here on, let me get this first. Here, the distance that we're talking about is going to be the distance from the center of the planet to the center of the sun. But you can see that the distance from here to here is going to be different than when this planet rotates around here, and the distance from here to here. This is much larger than this. So what we do is we take the average distance of the planet's orbit. So that's what that D is. This D is going to be the average distance, and this D. So what the third law of Kepler's law says, the square of the time period, which is right up here, so it's T squared, of one rotation divided by the average distance from the sun cubed is always a constant value. So what we can do is we can compare this for one object with it to another object, and it's always going to be the same. So the time period of the Earth squared over the distance the Earth is to the sun cubed is going to equal the time period of Mars squared over the distance Mars is to the sun. So we can do some calculations that way. So those are Kepler's third laws. Let's try an example using Kepler's third law. Okay, our example, we have a large planet. It's orbiting a distant star. It's discovered. Okay, so we have no idea what this planet is. We don't know anything about the star. The planet's orbit is elliptical, and its period is 105.5 days. So maybe they were watching it for 105.5 days. They found out that's how long it took it to orbit that star. knowing that the distance from the center of the Earth to the center of the Sun is 1.5 times 10 to the 11th meters, we need to find the distance that this new planet is from the star that it's rotating around. So we can use Kepler's third law. Our given is the time period of this new planet, which is 105.5 days. We know that the time period for Earth is 365 days, and we know that the distance from Earth to the Sun is 1.5 times 10 to the 11th, and these are given. Our unknown value is the distance that that new planet is to the center of its star that it rotates about. So Kepler's third law right here says that the time period of the new planet squared over the distance the new planet is to its foci or its star cubed has to be a constant, which has to equal the same as any other planet. But we're going to choose Earth because we know the time period of one revolution of Earth around the Sun, and then they were given us the distance the Sun is to the Earth cubed. So right here, what I'm looking for is the distance of the planet right here. So if I cross multiply here, I'm going to be able to get my dp cubed up here, but then I'm going to take this down here, so I have te squared, I have t planet squared times the distance of Earth cubed over the time period of Earth squared is going to equal the distance of that planet cubed. So to find out the distance of the planet, I'm going to take the cube root of this whole thing, so I end up right here. Now I'm going to plug in all these numbers. The time period for one rotation for this planet is 105.5, but I'm going to square it. And the distance from the Earth is 1.5 times 10 to the 11th, and I want to make sure I cube it. And I'm going to divide it by the time of one revolution around the Sun of the Earth, which is 365, and we're going to square that. And then we take the cube root of it, and we end up with 6.56 times 10 to the 10th meters. That is the distance that this new planet is from its rotating, the star that it rotates around. Okay, so tomorrow in class, we're going to do a little bit of a lab on elliptical orbits. Don't forget to do the Edline assignment tonight, and we'll see you in class tomorrow. Bye.